In today's practical session, we will be discussing about sieve analysis. Sieve analysis is used as a technique to determine the particle size distribution of the given powder sample. Our aim for this experiment is to determine the particle size and the particle size distribution of the given powder sample by the technique called sieve analysis. To perform sieve analysis, we need sieve set, a standard sieve set, and the mechanical sieve shaker. Mechanical sieve shaker has a monitor with the setting systems where we can set the time for which this shaker has to be run. Coming to the standard sieve set comes in different sieve numbers. The sieve number represents number of pores per square inch. Suppose if this is the mesh and the mesh is having the sieve having the mesh. So per square inch, how many number of pores or apertures are present? Represents the sieve number. Sieve number represents the number of pores per square inch. Suppose if we consider this area, number of pores per square inch. So suppose if it is of 10 mesh per square inch, this sieve consists of 10 pores or 10 openings or 10 apertures. And for 230 sieve number, it consists of 230 number of pores per square inch. So as the sieve number increases, number of pores per square inch increases. So the pore size will be very fine. So fine powder will be obtained here and the coarse powder will be obtained on the top of the sieve. Let's see the working principle of sieve set along with the sieve shaker. Now, the sieving method here helps in the determination of particle size and also the weight distribution. Suppose if we consider a standard set of sieves which are arranged as a nest. Now the sieves are arranged in such a way that the coarsest sieve should be on the top and the finest sieve should be at the bottom. Below this the finest sieve, we will be having a pan to collect fine powder. Now this is the set of sieves to be kept on the mechanical sieve shaker. Now let's see how this sieve shaker or the sieve set helps us in determining the particle size and the particle size distribution. The given powder sample is placed on the top. Here, powder sample. So the given powder sample will be having different particles of different sizes. It might contain coarser particles, moderately coarse, moderately fine, and fine powder particles. So when we keep that powder sample on the top coarsest sieve, and when this set is arranged over a mechanical sieve shaker like this. We need to cover this with the lid, and below the sieve's bottom will be having a pan. Now when this is run for 20 minutes, now when it is run, now this equipment will undergo mechanical movements to and fro. So because of these mechanical movements, like it will be like shaking a bottle just like that. So the to and fro motions will help the powder sample to undergo passage between the meshes. So when the shaker undergoes movements, to and fro movements, the particles slowly will pass through all the sieves. The larger particles will stay here, and the lesser larger will stay here. Similarly, it will reach the bottom of the set. So when we see from the picture, we will be able to see the coarser particles will remain on the top, moderately coarse will be there. Similarly, size wise, they will be collected beneath the sieve. So for this experiment, we'll be taking 50 grams of powder and we'll be placing over the top, and we'll be running this equipment for 20 minutes. The powder retained on each sieve is weight. And the thing is like for pharmaceutical purpose, this sieve, the wire, the sieve, the mesh is made up of wire cloth, or it might be woven with the metallic wire, finely woven, which include brass, bronze, steel, other suitable materials. But mostly we'll be making use of stainless steel because it will be non-corrosive and it cannot react with few chemicals. Like if our drug particles consist of iron oxides or iron substances, then there'll be no reaction between the metals and the drug. So stainless steel is mostly preferred. Now let's see what are the various factors that influence sieving. And of course, the weight of the sample, duration of the shaking, no, the optimum time for the experimentation will be 20 minutes. And also type of motion, whether the sieves are undergoing to and fro motion or rotatory motion. Like for example, if this is the sieve, okay, and if we have placed this on the mechanical shaker, normally this sieve will be moving to and fro like this, or else in few equipments there will be to and fro motion, and again this will be rotated like this, a rotatory motion and to and fro motion. So the type of motion also plays a major role. Now care must be taken that the duration should not exceed 20 minutes, and also the intensity of shaking should be standardized, it should not be more. And again, during this vibratory motion, there might be chances of clumping of particles or the aggregation of particles. Why? Because of shaking, there might be attractive forces or the electrostatic forces that exist between the particles, and because of these forces, all the particles might come together to form lumps or the aggregates. So the whole purpose of the experiment will be lost. So care must be taken so that the powder should be dry enough, and the equipment should not be run more than 20 minutes. And how this sieve analysis is applicable in the pharmaceutical industry. What is a need? Apart from determining the particle size and particle size distribution, how this is useful for a pharmacist. Now, to prepare a tablet, we need to have in the preparation of dosage forms like tablets and capsules. This is actually most widely used. And let's see what is the importance of sieve analysis in the tablet dosage form preparation. In the tablet manufacturing, actually, we will be considering the uh, substances like drug substance and the excipients in the form of granules. Now, to prepare a tablet, we need to have at least 15% of fine powder. So apart from the granules, which are supposed to be compressed to get the tablet, we need to add at least 15% of fine powder, 15% of total composition. For example, say 100%. So in that, 75 should be your granules. 85% should be your granules or coarser particles, and 25% should be 15% should be your fines. So what is the need of adding fines? Just to improve the mechanical stability or strength of the tablet. For example, say so if we to compress a tablet. Now let me give one example. Suppose if we take the particles of a coarser size, and if this is compressed to get a tablet, now because of the larger size, there might be chances of occurrence of air spaces between the larger granules. So when we are compressing, the air gets entrapped, and the mechanical strength of the tablet will be very weak. And if we add fine powder to it, the fine powder gets into the spaces of these air spaces, and when this is compressed, now we are having the larger granules and also fine particles. Now when this powder is compressed, which is having larger granules and also fines, then the mechanical strength of the tablet will be improved. So that is why the fine powder obtained by this sieve analysis can be added into our formulation to improve the stability of the formulation. So when we are doing the sieve analysis, we are able to differentiate the granules or the powder particles according to their sizes. So coarser powder, less coarser powder, more coarser powder, fine, very fine powder. So we need to choose accordingly to improve the stability of the formulation. This is how sieve analysis plays a major role in the manufacture of tablets and capsules. Now for the sieve analysis, it is very important to have a knowledge on the sieve set. According to United States Pharmacopoeia, that is USP, we are having different sieves having different sieve numbers. Say sieve number 8 represents 8 pores per square inch. So each pore, this is a sieve and this is a mesh. This each square represents the pore, and per square inch how many pores are there represents the number of sieve. Sieve number 8 represents 8 pores per square inch. So each pore size would be 2380 micrometers. So as the sieve number increases, number of pores increases. See, number of pores. As the number of pores increases per square inch, what happens to the pore size will be decreased. So it will be in the range of 105 micrometers. So the powder up that pass through this 140 sieve number would be very fine. So the coarser powder will stay on the top of the sieves and the finer particles will be collected at the lower sieves. Now this concept is used to determine the particle size and the particle size distribution. This is the mechanical sieve shaker. Now let's see. Now let's select the standard sieves and let's place the sieves according to their sizes. The coarsest sieve will be placed on the top. Means lesser number would be at the top and the greater number would be at the bottom. Beneath this, we'll be placing one pan, and above this, we'll be closing it with a lid and we'll be tightening the knobs. Now here, before closing this lid, we'll be adding 50 grams of sample. And then this equipment machine is run for 20 minutes. During this 20 minutes, all this sieve shaker will be moving to and fro. And after, as it is preset to 20 minutes, after 20 minutes, this will get automatically stopped. And then after that, the samples are collected from each sieve. Suppose we have added 50 grams here, and the coarser particle will stay on the top, and the lesser coarser will be on this pan. Similarly, they will get rearranged according to their sizes and they get retained on the sieve. The very fine powder that pass through the last sieve will be obtained on the pan. Now we are having different samples that are collected beneath the sieve. Now let's see here. Suppose this is the sieve, okay? This is the coarsest sieve, or say sieve number 5, and here would be sieve number 10, sieve number 5, and here would be sieve number 44. Now let's take. So the material or the particles which stay on this sieve would be a larger one, and the powder particle which pass through sieve number 5 will be lesser than the pore size of this one and larger than the pore size of this one. See, here it will be, and still it will be here like this. So when we see this in detail, the particles which retain on sieve number 5 are said to be oversize for sieve number 5 because it did not pass through this one, it retained on sieve number 5. And the particles which pass through the sieve number 5, these are known as undersize for sieve number 5 because it passed through the sieve number 5. And at the same time, these are said to be oversize for sieve number 10. And these particles are said to be undersize for sieve number 10 and oversize for sieve number 44. This is how we need to categorize the particle sizes. And again, the particles retained on each mesh are taken separately and weighed. So weight of the powder particle retained on each mesh is noted. So now the powder particles retained on the first mesh is taken and weighed down and write it down. Note down the weight of the particles retained on the sieve number 5. Similarly, next sieve number. Take out the particles, take out the sample and weigh it. So now at the end of experiment, we are able to categorize the given powder sample according to their weights. So say the coarser particles are present in the percentage of say 5%, like that. So weigh all the samples and report the weights written on each sieve. Now from this data we are going to analyze the size distribution by making plots, normal plot, normal log plots, cumulative frequency plots. Now this experiment and this explanation is going in parallel with the theory, for which you can correlate with the video that included in the theoretical part of micromeritics. Now this is the tabular column for the calculations. Suppose this is the sieve number. Sieve number we have taken a sieve set ranging from 10 to 120, and the pan over which very fine powder will be obtained. Aperture size, for aperture size we have, see, the standard values. So for 10 the aperture size is 2000 micrometers, for like that. So for each sieve number we will be having aperture size. So this two columns will be, the data will be obtained from the monographs. And the next column is the arithmetic mean size of opening. The arithmetic mean size of opening. Now as we have discussed, like oversize and undersize, to avoid these confusions, we have come up with one parameter known as arithmetic mean size of opening. How can we calculate the arithmetic mean size of opening? For example, this powder has passed through sieve number 5 and retained on sieve number 10. Now how can we know this is undersize for sieve number 5, oversize for sieve number 10? Now how can we calculate the mean size of the opening? Nothing but the apertures, pore size. The pore size of this sieve plus pore size of this sieve by 2. So nothing but the average of the pore sizes of the above sieve and the below sieve. So for example, if a powder is passing through sieve number 22 and retained on sieve number 44, okay, so sieve number, say this is sieve number 22 and this is sieve number, so he's passed through sieve number 22 and retained on 44. Now how can we give the arithmetic mean diameter? So let's check for the monograph what is the pore size for sieve number 22 and pore size for sieve number 44. So some value, this value plus this value divided by 2 gives the arithmetic mean of opening. So we'll be getting the value here. Now the log value of this column will be the log arithmetic mean. Just to avoid errors, we'll be taking the log scale, and also log scale is actually considered just to get the better graphical representation. And the next column is weight retained on the sieve. So for each sieve we'll be weighing the sample retained on the sieve. Percentage weight retained, undersize means on the next sieve. Cumulative percent retained For example, here if it is 2 grams, and here if suppose if it is 2 grams, and here if it is 3 grams, so cumulative percent retained would be here 2 grams, here it will be 5. So we need to add the cumulative percent. The weight over size will be on this column. Now the average diameter of the powder particle is given in your report. Now how can we analyze these observations and report the average diameter of the powder particle? We got all these parameters, all these observations, right? Now how can we convert or interpret this data and get the average diameter? Let me explain with an example. Suppose this is the data you get from your experiment. Say, suppose we need to calculate the average diameter for the given powder by sieve analysis. So from this analysis we are able to determine the size, means the pore size. Suppose if the particle is passing through this mesh, now we can say that the particle size of this will be in equivalent with the arithmetic mean. We have considered this pore opening and this pore opening. So average of these two opening sizes will represent the particle size. So that value we'll be writing here. Now we have taken just 3 values. So we have taken like that, we are having 3 values and frequency weight based on the calculations here. Percentage. Now we have considered this value and this value. So the mean size here, now the data is given, it will be given from the experiment. Now how can we interpret this data and get average particle size? These two data, and then the third column would be weight size n into d, frequency weight into diameter, mean size. So for each n c into d, this is d, right? And this is n, weight retained, n into d. That is how we'll be getting weight size n into d, that column. Now sigma n, summation of all these values, n into d, summation of all these values. Now the average diameter of the particle is given by the summation of sigma n into d by sigma n, this value by this value. So from that we be able to get the average particle size. Now when you're going through this video for sieve analysis, kindly go through the theoretical part of micromeritics, in which sieve analysis is explained. So the explanation in the theoretical part and the practical part goes parallel. Kindly go through both the videos so to get the concrete explanation. So this is about the sieve analysis and the interpretation of the data from the sieve analysis. See, from the sieve analysis we are able to calculate the particle size and also particle size distribution, weight distribution. how much amount of how much percent of powder consists of particle particle size. Like that, the data can be easily analyzed. So this is about the sieve analysis. If you have any doubts, you can contact me through the mail. Thank you.